The Open Systems Interconnection Model, also known as OSI, is a way to know how a network is going to be structured based on how it communicates with other elements in the network. So this is similar to the TCP/IP model in that these elements are going to be divided into discrete layers based upon a specific order. And the order is going to determine the interaction between the layers. And so each layer supports the layer above it. At the same time, it's going to be supported by the layer below it. So the data link layer is supported by the physical layer, but it supports the network layer. And looking at this table, we have layer 1, which is going to be the physical layer. It defines connections between devices and the physical transmission media. So this is going to be our cables and wiring and basic network devices like our hubs, repeaters, or adapters. After that, we have the data link layer. So this provides a link between two directly connected nodes, as well as detecting and fixing errors that happen in the physical layer. So this is going to give us our point-to-point protocols that provide us with encryption and authentication and stuff between nodes. This will be our Ethernet, which is the basic standard for local area network connections. Then we have the network layer. So the network layer is going to provide the protocols for transferring data from one node to another in a system with multiple nodes having unique addresses. Basically our IP protocol, right? Our internet protocol. And that's going to manage host address over the internet. Then we have ICMP, which is also at layer 3. So this is going to be testing for communications between devices and sending those ping messages. And then we also have the Routing Information Protocol, or RIP, which is going to prevent loops in routing by limiting the number of intermediate routers between a source and its destination, right? So this is going to decide how we're going to traverse the internet to get to the destination in the shortest amount of time. Then we have the transport layer. So the transport layer is going to control the reliability of data transmission between the nodes on a network for the benefit of the layers above it. So first we have the TCP protocol, so that's Transmission Control Protocol, and this is going to be our connection-oriented guaranteed delivery protocol. So remember, that's SYN, SYNACK, SYN. So it not only does it send data, but it waits for that acknowledgement and fixes any errors if possible, so it will go back and send that packet again. We also have the User Datagram Protocol, UDP, and that's going to ensure that we have a constant transmission of data packets, which are called datagrams in UDP. And so it bypasses any error checking because that will cause delays. So if we're streaming a movie, it's just going to continue. If we're having a voice over internet call, it's just going to continue. And then if you have a skip, that's called a jitter. It's not going to go back and retrieve that packet. We also have layer 5. That's going to be our session. Well, that's going to control the connections between computers through checkpointing that the connections are, when they're terminated, they can be recovered. So here we're going to have our network file system, NFS, and this is going to allow clients to control files or access files on a network as if you were accessing local storage. And then they have socket secure as well, so you'll see that as SOCKS. And that's going to route data packets on a network through a proxy, and it also has authentication. Then we have the presentation layer, which transforms data into a format that can be understood by the programs in the application layer. So basically, it's going to present it into code for our application layer to be able to read, right? Because we are going from bits to packets to TCP or UDP datagrams, etc. Until we get up to all the way to the application layer, in which it's going to be rendered in a language that our application can read. And then finally, we have our application layer, and that's going to enable us as the client to interact with the software. And so here we'll have stuff like Hypertext Transfer Protocol, HTTP, so that way we can view the information on the World Wide Web. We'll have FTP, which lets us transfer files, remote host, and a workstation over TCP, and the domain name system, which is going to translate our human domain names into an IP address. when it comes to the OSI model and security, understanding these layers of the OSI model is going to make it easier for us to identify threats and know how these threats will possibly impact our network. So securing our network by layers is going to be a useful strategy in securing the entirety of the network, as these layers are going to be designed to integrate with one another. So if the most fundamental physical layer fails, then the rest of these are most likely going to fail as well. And at the same time, if there is an attack at the application layer, then the layers beneath it will likely fail as well. Internet Protocol Suite. So the TCP, Transmission Control Protocol, Internet Protocol, IP. So this is going to be the native support protocol of the internet, and this is required for internet connectivity. So TCP/IP is named after the original protocols that were included in this suite. So first off, we have IPv4. IPv4 has 32-bit numbers assigned to computers over a TCP/IP network. It has some bits are going to represent the network segment, and the others are going to represent the node itself. And these are done in 4-bit octets that can be converted into decimals. So we would have done a lot of that in our networking class. And then we have IPv6. That's the newer one, because IPv4, they are pretty much out of IPv4 addresses. There was only 4 billion of them. IPv6 has many, many trillions. So this is going to be a 128-bit address space. It has additional features beyond IPv4. And there are 8 groups for digits, hexadecimal digits. And so the leading zeros will be omitted when we write these out. And then groups of consecutive zeros can be replaced with 2 colons when we write these out as well. You will see some conversions of IPv6 that you need to do, and mostly what you need to do is be able to get rid of those zeros and know where to place the colon if they give you an IPv6 address. So it's not compatible with IPv4. It's not as widely adopted. However, a lot of people are implementing it in the United States, and places like China and other areas in East Asia are already using it. So IPv6 is the future. So it is a good idea for us to have a decent understanding of it, at the very least, how to write it out. And then we have DHCP. So DHCP is a protocol used for address allocation. So DHCP is going to assign automatically IP addresses for our network computers, except for ones that are already assigned a static IP address. So the DHCP server, when the DHCP server or router is going to hand out those IP addresses to a computer or smartphone or whatever as soon as it connects to the network. So then your smartphone or whatever becomes 10.0.0.26 or something. And your other smartphone becomes 43, right? In addition to DHCP, there's something you guys should know called a PIPA. And so that means automatic private IP addressing. And that's a Microsoft Windows service that enables DHCP client computers to start up TCP/IP when there's no DHCP available. These DHCP clients are going to get an address if the DHCP server doesn't work, or when the computer itself doesn't have any connectivity. And so it self-allocates an address between 169.254.0.1 and 169.254.255.254. The only reason I bring this up is you may see this on the test itself. One of these addresses, these 169 addresses, is going to indicate that you're not, most of the time, that you don't have internet connectivity, because DHCP did not hand out an IP address for you. So that's just one thing to remember for your test. This is usually because you did not get an IP assigned to you. The domain name system. So the domain name system is the primary domain name resolution service on an internet and private IP networks. So the DNS is a hierarchical system of databases that map computer names to IP addresses. So these DNS servers are going to store, maintain, and update databases. They respond to client requests and translate human intelligible names into IP addresses, and work together to provide name resolution for all clients. So when we type in CompTIA.org in the URL, the domain name server looks at that request and it goes in basically what it is, its phone book, and it sees, okay, what is CompTIA.org's IP address? Then it finds CompTIA.org's IP address and it serves back to your browser CompTIA.org's domain IP address, and that's what you're really looking up. Just like in your phone book, you're not really calling mom, you're calling the phone number that you've saved as mom. And so it's the same thing here with the DNS server. It's not, when you go online and you type in the URL, you're not really going to google.com, you're going to 8.8.8 or something like that, right? And because that's what the DNS server gave you. So a lot of times in any corporate network, the DNS is going to be targeted first, and there are several applications that are going to be available that help to secure the DNS. And so a lot of times we'll want to place the DNS server in a DMZ. We'll want to set firewall rules to block any incoming non-essential service requests. We're going to want to use something called DNSSEC, which is going to provide authentication of DNS data and uphold our DNS data integrity. And we're going to want to back up DNS and save the backups into different geographical locations. The reason we're going to do this is because people, when they want to attack the DNS system, because it's easy to redirect you to somewhere that you don't actually want to be, and they can give you a false google.com, right? You decide you want to go to google.com, but instead of your computer going to 8.8.8, it goes to 74.34. whatever, and that is a false Google, and you're going to go ahead and try to log into your Gmail, and what you've really done is given somebody your credentials. So that's why people a lot of times will try to attack the domain name system. Hypertext Transfer Protocol. So HTTP is going to be a TCP/IP protocol that is going to enable clients to interact with websites and connect with them. So it's responsible for transferring data on web pages between systems, and HTTP is going to define how the messages are going to be formatted and transmitted, and what actions our web server and the client's browser should take in response to different commands. Next up is SSL TLS, and that is Secure Sockets Layer and Transport Layer Security. So these are both security protocols that combine digital certificates for authentication with public key data encryption. So both protocols are there to protect sensitive communication from eavesdropping and tampering by using a secure, encrypted, and authenticated channel over a TCP/IP connection. So SSL TLS is going to be included in all current web browsers, and it can connect to an SSL or TLS server. What we are really dealing with right now is usually TLS, Secure Sockets Layer, has been pretty much deprecated. SSL TLS, I just want to get that out the way. But this is going to be a server-driven process that works with all current browsers. Okay, so SSL TLS accelerators are a hardware device that offload encryption to calculations from a server to reduce overhead for that server, right? So this enables the server to perform its primary duties more efficiently. And so an SSL TLS accelerator is going to be like a hardware card that's plugged into a server that needs encryption services and can go ahead and can handle that duty for it. It's able to sit there and handle those encryption calculations for it. So in the Secure Sockets Layer handshake, what we're going to do is we're going to request a connection to a server from our web browser, and then that server is going to send back the certificate along with this public key. And then you, as the client, are going to send back a session key or a shared key that's encrypted with that public key for you guys to continue your conversation. So HTTP Secure is HTTPS, and so this is going to be a secure version of HTTP, and this is going to support web browsing communications by providing a secure connection between the web browser and a server. So it uses SSL TLS to encrypt the data all of these web browsers that we use nowadays are going to support it, and these web addresses are going to be HTTPS. So for your security, you should probably always try to go to a website that is HTTPS, but sometimes some websites, some major websites, are still using HTTP. I used to show my class NYU's website, and that was HTTP up to like a month ago. And that is a major university. Secure Shell. So Secure Shell is SSH, is protocol used for secure remote access and secure transfer of data. SSH is going to consist of a server and a client. So most SSH clients are going to implement some sort of terminal emulation software in order to open a secure terminal session on a remote server. So what that means is, like, say you're getting into Linux and you're on Windows, you're going to emulate Linux on your Windows machine when you start that SSH process. So the entire session is going to be encrypted, and it is the preferred protocol for FTP, and it's used in Unix and Linux. It's in Mac. However, we need third-party software called PuTTY on Windows, and then you'll go ahead and you'll emulate that software. Along with Secure Shell, there is another older protocol called Telnet, and Telnet is going to allow us to initiate a remote connection over TCP/IP, and the most modern operating systems support Telnet. However, it's discouraged. If you come across a question that asks about incorporating Telnet, you should not, because man-in-the-middle attacks are pretty easy with Telnet, because Telnet doesn't require any sort of authentication between the client and the host. So avoid Telnet where at all possible. Simple Network Management Protocol. So that is SNMP, and this is going to be a service used to collect information from network devices for diagnostic and maintenance purposes. So SNMP is going to have two major components. This is going to be the management systems and agent software. The agent software is installed on a network device like a router, a printer, a server, and then the agents send information to the SNMP manager. And so the SNMP manager can then notify the administrator of any problems and store information for later review, things of that nature, right? And so the newest one is SNMP version 3, which encrypts the communications in order to support CIA, right? So these agents are going to send information to the management system in order for you as the admin to manage those networking devices. Real-time transport protocol. So that is going to be RTP, and RTP is going to provide audio and video streaming over TCP/IP. So RTP is used in things like voice over internet protocol, web conferencing, content delivery, all sorts of stuff. And so RTP uses UDP to carry the media with low overhead. Low overhead meaning it's not strenuous on the system, and it works with RTP control protocol in order to have quality of service while streaming our media. And we also have secure real-time transport protocol, and this is going to add encryption services to RTP to uphold our authenticity and integrity. It also helps us to protect against replay attacks. Internet Control Message Protocol. So this is our pings, right? A lot of times. So this is an IP network service that is going to report on connections between hosts. It's used for simple functions like ping. So attackers are going to use ICMP packets to check for host availability once they got into a network. And this information is going to help them to decide which way they want to go within a network. Attacks using ICMP are going to be flooding a system, such as a Smurf attack, which we would have done in NetSim, along with reconfiguring routing tables, because you can forge these packets pretty easily. Internet Protocol Security. So this is IPsec. This is a set of open, non-proprietary standards that we can use to secure data as it travels across a network. So IPsec is going to use different protocols to provide data authenticity and integrity, um, all that jazz, in order to protect against eavesdropping and sniffing. So unlike SSL, TLS, and SSH, this is actually going to work at the layer 3 model of OSI. So it is not application dependent. The other ones actually are. So the two main protocols in IPsec are going to be an authentication header, which is going to provide authentication for the origin of the transmitted data, as well as integrity and protection for against replay attacks. And then it also has encapsulation security payloads, which is ESP, and this is going to provide the same functionality as an authentication header, but it also adds encryption so that we have confidentiality in our transmitted data. So a lot of operating systems are going to support IPsec. It's usually going to be stuff like Windows Server, Linux, Unix, etc. And then a lot of networking devices, such as routers, are going to support IPsec as well. So it's currently an industry standard. However, it's going to be implemented differently in each operating system and device. NetBIOS, Network Basic Input Output System. This is a service that enables applications to properly communicate over different computers on a network. NetBIOS has three basic functions: communications over sessions, connectionless communication using datagrams, and then name registration. So attackers can exploit NetBIOS by obtaining information about a system, such as the registered name, the IP addresses, whatever operating system or applications are being used. And so in order to harden NetBIOS against these attacks, we need to implement strong password policies. We need to also probably limit root access on the networks and also disable any null session capabilities. When it comes to file transfer protocols, we have FTP, which is going to enable the transfer of files between a workstation and a remote host. So with FTP, a user can access the directory structure on a remote host. They can change directories, search and rename files, and download and upload files. But then we have SFTP, and that is Simple File Transfer Protocol. And this was an early unsecured version of FTP, and it's now obsolete. And also we have Trivial File Transfer Protocols. That is going to be a limited protocol used primarily for automating configuring of boot files between machines and firmware updates for routers and switchers. And it offers basically no security. So the protocol is pretty much only used on local systems instead of the internet. We also have FTP over SSH, and so that's also called Secure FTP. And so FTP over SSH is a secure version of FTP that uses a SSH tunnel for its encryption to transfer, access, and manage files, and it's primarily used on Windows. Then we have Secure Copy Protocol, that's SCP. This is going to use SSH to securely transfer computer files between a local host and a remote host. And this is going to be or also it could be between two remote hosts. So SCP can be SCP can also be implemented as a command line utility that is going to use SCP or SFTP, and that way it's going to perform secure copying. And this is primarily used on Linux and Unix. And finally, we have FTP Secure, or it could be also called FTP SSL, and this is going to combine FTP with SSL TLS. Email protocols. So there are two main protocols that are going to be used in the transmission of emails, and this is going to be Post Office Protocol, which is POP, and Internet Message Access Protocol, which is IMAP. So IMAP is more recent, and it was created to fix some of POP's problems, and this includes like the ability for multiple clients to access the same inbox, the ability to keep track of a message's state, right? And so neither protocol is going to natively support encryption. However, there's also Secure POP and Secure IMAP, and these are extensions that enable these email messages to use stuff like SSL TLS. And then we also have secure multi-purpose internet mail extensions. So that's SMIME. And then SMIME is an email encryption standard that adds digital signatures using public key encryption to a traditional multi-purpose internet mail extension. So multi-purpose internet mail extension defines several advanced characteristics of email messages and that had previously been unavailable. This would be like the ability to send stuff like character sets that are not ASCII, like um, regular Latin letter keys, and also the ability to send non-text file attachments, so like pictures and stuff like that. So it's going to help to uphold CIA information and non-repudiation. Additional networking protocols and services. We have telephony, so that's going to provide our video and voice communications over a distance. And so the most common one here is going to be voice over internet protocol, VoIP, and that is when voice traffic is transmitted over an IP network. And we also have web conferencing platforms that are going to use VoIP with video. Then we have routing and switching. Routing and switching protocols are going to define the language that these devices use to communicate. So common routing protocols are going to be RIP, which is Routing Information Protocol, and we also have RIP v2, and then RIP v2 is going to support security by enabling password authentication and it also uses a key to authenticate routing information to a router. And then there's also even more improvements on that, and that's going to be Interior Gateway Routing Protocol, which is IGRP, and Enhanced Interior Gateway Routing Protocol, which is EIGRP. So one of the most common switching protocols is going to be Spanning Tree Protocol, and this is going to attempt to prevent network loops by disabling links wherever it's necessary. That way we don't get stuck in a loop. Then we have time synchronization. So time synchronization is going to ensure that software and services are coordinated properly and that all types of events generated by a system are accurate in respect to the events that occurred. So the most prominent protocol that's going to provide time synchronization is going to be Network Time Protocol, and this is going to synchronize computers to Universal Time, UTC. And this is going to contact a public time server. So this is how your phone and your computer and all of that is able to be all at the same time. It's always synchronized nowadays. We don't have to set our watches. All right, so we can set up our own local time server and avoid having to configure a firewall to allow NTP traffic. However, it's kind of easier just to let it do it. And then we have subscription protocols. So subscription protocols allow services. Subscription protocols are going to enable a publisher to send a particular message along a particular channel. And so any clients that are subscribed to that channel are going to receive that message. So this enables the publisher to send messages without knowledge of who the actual recipient is. So that'll be something like RSS. So that's Rich Site Summary. And that's the most popular one. This enables users to subscribe to a feed of a website that interests them. And then the participating website is going to automatically publish new entries to that website's feed. So that's going to be like, I use it specifically, I used to use it for Craigslist. And so when I want to know something about like maybe a free TV or something like that, I will subscribe to the RSS feed. That way it's going to update me without me having to search for it. It will send that on to an email or something like that, and I'll get a feed of all the new TVs that are currently posted to Craigslist. Ports and ranges. So ports are going to be the endpoint of a logical connection. So client computers connect to specific server programs through a designated port, and then all ports are assigned a number from 0 to 6,500 and or what is it, 65,535. So there are assigned internet assigned numbers authority, which is going to separate port numbers into 3 different blocks. So we have our well-known ports, which are going to be pre-assigned, and those are 0 to 1023. So these are widely used in core services. These are stuff like FTP, SSH, DNS, HTTP. And then we have registered ports, and that's going to be 1024 to 49,151. And that's going to be available to services requesting registration. And attackers may scan those ports, but they often attack well-known ports. One of the ports we would know about in this one would be RDP, and that's going to be able to remotely connect Windows hosts. And then we have dynamic hosts, and that's going to be assigned by the operating system to client software as needed. Attackers may scan for these, but a lot of times this is going to be something like we'll connect out on a certain application to the internet.